dash of x, or the derivative with respect to x, 0 plus h at 0 minus f at the origin divided by h. Start substituting, I will use this guy. So if I make a substitution of 0h and 0, this is going to be 0 plus h to the power of 2, which is going to be h squared. Minus 0, it will be eliminated. Divided by h plus 0, so it's h squared over h. And the value of the function when h equals 0. When, the value of the function at the origin. The value of the function at the origin is going to equal to 0 and 0, so it's going to equal to 0 as you can see. When x equal to negative y, then the result will be zeros as you can see. So from this relation, okay, from this relation, you will have h squared with h, which is going to be just only h, with h, the result will be 1. If I want to get the derivative in the y direction, I will do exactly the same. It's going to be a 0, 0 plus h minus the f at the origin divided by h. And also will lead to negative h squared over x. The negative sign are coming from here, because you are substituting with 0, then 0 plus h. 0 plus h will be h to the power of 2. Then dividing also, it will be negative 1. So if you are differentiating this function from the x direction, it will be positive 1. From the negative 1 direction, or from the y direction, it's going to be negative 1, as you can see. Also, compute f dash y at 0 and 0. So I will repeat everything. I will get the derivative of this function, but remember, I'm doing the y derivative, okay? So once more, if I want to do this, all I have to do is to get the derivative of this function with respect to y, then getting the value at 0. In this case, I'm not going to use the law, I will use my skills in partial derivatives. The general rule of partial derivatives, I will differentiate with respect to the choose variable only, considering the other variables as constant. So if I want to do this, it's going to be f with respect to y, which is going to equal to. This guy is a constant. The only thing that will be differentiated is y. The derivative of y is equal to 1, so it's going to be 1 times ln of an x plus e. That's the derivative of this function at y. But I don't need the main function. I will need to evaluate f dash y at the origin. So which leads to that f dash at the origin, start substituting, it will be 1 times ln 0 plus e. And as you know, ln e is equal to 1. So the result is equal to positive 1. So I made the derivative first, then I made the substitution with the origin, as you can see. So once more, this is y plus 2 ln x plus e. I will do the derivative with respect to y. It's going to be ln x plus e. I will make the substitution, replacing x with 0. So that's the result, which is positive 1, as you can see. Okay, once more, I want you to remember, needed in the case of functions of several variables, Rn into R, or in the case of Rn into Rn. Those are the partial derivatives and how they work together either in the x direction or in the y direction. I will give you more examples just to increase your ability in the partial derivative. For example, if I have x equal to x squared y, 3xy squared plus 4y. If I want to differentiate this function with respect to x, so I need to get f sub x. How it's going to be? I will make the derivative with respect to x considering y as a constant. So Omar, this one, trying to differentiate with respect to x. So it's going to be 2x, y. Once more, differentiate with respect to x. So the derivative of x is equal to 1. So it's going to be 3 of y squared. If I want to get f sub y, can you do it? F with respect to y. So I will differentiate with respect to y considering x as a constant, as a numbers. So differentiating with respect to y will give you x squared. Then plus, differentiate with respect to y, so it's going to be 6x times y. Differentiate with respect to y, so it's going to be positive 4. But what if I want to get the second derivative or the third derivative? If I want to get the second derivative, I will be between options, having f in the two derivatives with respect to x. So now I can get simply f of x, which means I will differentiate f 2 times with respect to x. By the idea, it can be symbolized by this manner, partial 2f, partial x squared, which means I will differentiate f 2 times in the 2 times with respect to x. Differentiate once more with respect to x. Do you have x's in here? No, so it's going to be 0. Do you have x in this part? Yes, the derivative is 1, so the result is 2, 1. Okay, let's get f y sub y, which means you will differentiate this function 2 times, but with respect to 1. So this guy is going to be 0, and that guy is going to be 0. But this part will deliver 6x for you, because the derivative of y is equal to 1 times 6x. Right, can you get me f of xy, which means I will differentiate 2 times, partial to f, partial x, partial y, which means I will get the derivative of y for the function which is already differentiated with respect to x. So all I have to do in this case is to take the function which is differentiated with respect to x, then I will replace, I differentiate the result with respect to y. Start the differentiating with respect to y. Differentiate this guy, the derivative of y is 1 times 2x, which is 2x. Differentiate with respect to y, so it's going to be simply 6y as you can see. Also, I can get f of yx, which means partial 2f, partial y, partial x, which means partial x for the derivative of f with respect to y. And in this case, I will take the derivative with respect to y, and then differentiating it with respect to x. Start differentiating with respect to x, so the result will be x squared will deliver 2 over x, and the x in here will be equal to 1 times 6y, which is 6y. As you can see, if the function is continuous in derivative, the mixed derivative, sometimes we call f of x and y, the mixed derivative, which means you are differentiating first with respect to x, then with respect to y, or vice versa. Differentiating first with respect to y, then with respect to x. خلي بالك يا عمر, this is essential, because you will need it down the road. So, for the first derivative, I get f sub x, f sub y, which means I'm differentiating with respect to x, or differentiating with respect to y. For the second derivative, how many I can do? I can do 3. In the case of functions, 2 variables. F of double x, f of double y, or f of xy, or f of y of x. Okay? So very simple. All of this is well written in your PDF. I've already sent it to you previously. For the work of this week, you already have the PDF and the lectures on, I will upload them after we finish the shop. So, mainly, this is going to be the partial derivative with respect to x and y. This is partial f, partial x for this function. So once more, I will differentiate with respect to x only, considering every y as a constant. That's going to be the result. I can get it from the beginning. It's going to be 2xy plus 3y squared, as you can see. That's the derivative with respect to y, so I'm differentiating this equation. This is going to be 4, that's going to be 6x over y. This is going to be x squared, that's the result. If I have them given, this is f sub x, f sub y, and if I want to get f double x, f double y, f of xy. If I want to get f double x, it means I will differentiate this one with respect to x. F double y, I will differentiate this guy with respect to y. f of xy, I will take this function and then differentiate it with respect to y. Also, in a similar manner, this is f of x. If I want to differentiate with respect to x, it's going to be 2y. If I want to differentiate this part with respect to y, it's going to be a 6 over x, as you can see, 6x. If I want to get partial f or fxy, it means I will differentiate with respect to y, the derivative with respect to x, which is going to be 2 over x plus 6y, as you can see, that's the result. Also, I have added more examples for you, like this guy, which is e to the power of x sine y plus then 1 plus x squared y. If I want to get the derivative with respect to x, I will differentiate x over. Differentiate with respect to y, the only thing will change is 1. So once more, if I want, I will do this problem, and it will be sufficient for this part, but I need to be sure that you are okay with everything. So if I want to get f of x, I will differentiate with respect to x. E to the power of x, the derivative will be e to the power of x times 1. So the second function is sine y is a constant. Plus, I will start differentiating. So derivative over n, which is going to be 1 over 1 plus x squared y. Derivative of x squared, it's going to be 2 over n times y, because y is constant. If I want to get f sub y, it's also really very simple. All I have to do is to differentiate this function, but with respect to y. In this case, e of x is a constant, times derivative of sine y, which is going to be cosine of y. Then plus, differentiating with respect to ln, which is going to be 1 over 1 plus x squared y. Then differentiating with respect to y, which is x squared, as you can see. If you want to push it far side, in order to get fxx, it is n double. I will start by differentiating this function, which is going to be e to the power of x times sine of y. Then plus, I will start differentiating this part. You can see that x, which is bivariable, appears in the denominator and in the numerator. So I will start as a function which is divided in each other, which means I will square the denominator, which is 1 plus x squared y. Then I will differentiate the denominator, which is going to come up to 2 over y, times 1 plus x squared y, then minus. I will differentiate the denominator with respect to x, which is going to be 2 over x y, times the denominator, which is 2xy. Then I will start simplifying everything. That's going to be the f sub double x. If I want to get f double y, it means this is the part that's going to be differentiated. If I want to get the derivative of the mixed derivative, then I will choose f of x and differentiate with respect to y, or vice versa, choosing f of y and differentiating with respect to f of x. All of this, or this problem, it's already solved. So just in a second. So this is my function after differentiating. Okay, if I want to get f of y, as you can see, only the parts that contains y is differentiated. So also in here, if I want to, after differentiation, simplify it, it's going to be x squared divided by 1 plus x squared y. So if I want to get f double x, means this function will be differentiated once more with respect to x. If I want to get f double y, so this guy will be differentiated once more with respect to y. If I want to get f of xy, so I will take this function and differentiate with respect to y. This is the derivative with respect to x. Okay, for the two parts, this is the second part derivative, which can be simplified. So that's the result that you will have for f double x. This is for f double y, differentiating. This is the first part. That's the second part. Then putting them both together in f double y. This is going to be the case. In the case of mixed derivative, I will take this function, then I will differentiate with respect to y. is going to be cosine y, then also this is going to be treated as two functions divided each other. Our square the denominator, differentiating the denominator times the denominator, minus differentiating the denominator times the denominator, and this is the result of your f of xy. Also, that's another problem, root x squared plus y squared. If I want to get the derivative with respect to x, with respect to y, then the next derivatives I can get easily, differentiating this once more with respect to x, differentiating once more with respect to y, or choosing the first function and differentiating with respect to y. I will leave this for you at this point. Okay. Now I want to talk about the gradient vector and the Jacobian matrix. The gradient vector and the Jacobian matrix are very, very important. The gradient vector usually are in the functions in several variables, which is going to be 3-dimension and more dimension than that, greater than that. But we have visualization for the 3-dimension one. So the gradient vector is the direction which is perpendicular on your graph. That's the shape of the gradient vector, the direction of the gradient vector. Generally, we will use the gradient vector in functions of several variables. So if I have a function which is defined on a1, a2, up to an, or x1, x2, xn, if I want to get the gradient vector, all I have to do, get all the partial derivatives, Omar, and substitute in the gradient vector. Of course, there is no exam. Will be away from the gradient or from the Jacobian. So you have to understand them, and they are really very simple. Once more, bottom line, Omar, I will have to differentiate the function with respect to its variables. Then putting all of them together in a row matrix. That's the gradient vector. And it is applicable in functions running from Rn into R, as you will see. So if I want, for example, get the gradient vector for this function, f of x, y, z, which is xy, then 1 over z. Can I get the gradient vector? Yes. The gradient vector in this case, how many variables, Omar, do you have? Okay, so the gradient vector will be, the gradient vector for f, it's gonna be partial f, partial x, partial f, partial y, partial f, partial z. That's the gradient vector. Why I have to do the 3 parts? Because if you remark, the function contains how many variables? 3 variables. Can you differentiate with respect to x? Yes, it's going to be x equal to 1 times all this value. So it's going to be y times len, okay, of 1 over z. Once more, Omar, differentiate all of this function with respect to y. So the derivative of y is 1 times x len 1 over z. So it's going to be x times len 1 over z. Omar, can you differentiate with respect to z? Yes, we can. Because len 1 over z, it is actually the minus of len z. Am I right? Is this correct? Yes, of course. Because len 1 over z is equal to len z to the power of -1. And we know from the probabilities of the logarithmic function that the power can go out. So it's equal to negative len over z. So once more, instead of writing this like that, it's going to be negative of xy len z. Now I can differentiate with respect to z. Differentiating with respect to z, we'll leave these two guys as constant, and I will differentiate len z, which is 1 over len. So it's going to be negative x y over z. That's the gradient vector. That's the gradient vector of f. But I need the gradient vector at the point 1, 1, 1. If I want to get the gradient vector at certain point, all I have to do after getting the gradient vector, substitute. So I need the gradient at triple 1. So let's stop substitute. 1 over 1 is going to be 1. Len 1 equal to 0. So this guy is going to be 0. Also, 1 over 1 is equal to 1. Len 1 is equal to 0. So that part is equal to 0 too. Substitute. So it's going to be negative 1. So the result for the gradient vector at triple 1, that's the gradient vector. At 1, 1, 1, it's going to be 0, 0, and negative 1. That's the gradient vector, as you can see. Now, from all of this, I can evaluate simply the value of the derivative of any function at the required point, simply as you can see. So, once more, I will get the derivative with respect to x, with respect to y, with respect to z. So the derivatives will be x times y ln 1 over z, then x times ln 1 over z, as you can see. Then differentiating this guy, which is going to be negative of 1 over z, that's the function. Substituting at 1, 1, and 1, making the substitution, you will end up having 0, 0, and the negative 1. Of course, as I told you, all our recorded lectures are on the YouTube. The final part in this lecture is evaluating the Jacobian. And this is very, very important to our. The gradient, if you remember, it's for functions in several variables. But the Jacobian will be working with vector valued function. Do you remember what's the vector valued function? The vector valued functions are the case of f running from Rn into Rm. And in this case, I will use the Jacobian. And the Jacobian dimension will be m sub n. This is really, very important now. I'm running from Rn into Rm. So the Jacobian will be m sub n, as you can see. So it's going to be a matrix m by n of the derivatives of the functions of the output was relative to the variables within the input, as you will see. Okay, so I will use the Jacobian. It's not up to you. You will use it in case of having the functions moving from Rn into Rm. It's all linear algebra. Once more. So the Jacobian matrix is a fundamental concept in multivariable calculus. We usually generalizes the derivative to functions of multiple variables. It plays a key role in differential equations, optimizations, and transformations. As we already know from the Jacobian, this is not the first time that we hear about it. Okay, it's from Rn into Rm, as I told you. And for an example, if you look to this function, بص كده يا عمر, it's running from R2, the input's 2. But the output is how many functions? How many functions? 3. So it's running from R2 into R3. So the input is 2, but the image will appear in how many functions? 3 of them. So if I want to get the Jacobian here, it's gonna be J function, which will be 3 times 2. How to formulate it? It's very, very simple. It's gonna be 3 rows in 2 columns. I will take the first function. That's the first function. That's the first function. I will call it F1. And that's the second function. I will call it F2. And that's the third component. I will call it F3. Each one of them will be differentiated with respect to the input. So I will get the first function, then I will differentiate with respect to x, with respect to y. So it's a partial F1, partial x. Then partial F1, partial y. That's for the first function. For the second function, let's do it together. So it's going to be partial F2, partial x. Partial F2, partial y. Let's do the same with the third one. Yalla yalla. Partial F3, partial x, partial F3, partial y, which is going to equal to, let's apply it. This is the first function. Differentiate with respect to x. It's going to be 2. Do you have y?
What?
Oh, you have what? So the derivative with respect to y will be? Okay, go for the second function. Differentiate with respect to x, which is going to be? Differentiate with respect to y, which is going to be? For the third one, do it to your own. It's going to be?
4x.
لأنك differentiate with respect to x. بعدين will be? لأنك differentiate with respect to y. That's the gradient vector. I'm sorry, that's the Jacobian, okay, for this multivariable function. Is it clear?
Yes, it's clear.
Is it difficult? No, it's really very simple. Okay, so once more, I will use the Jacobian just only in the cases of having functions in several variables, as you can see. So, once more, that's the general rule of f of x1, x2, xn. This is f1, f2 up to fn. I will differentiate each one of them with respect to the input variables. This is the shape of the Jacobian function. If you look to this problems, can you speculate the dimension of the Jacobian or the gradient vector? Jacobian or gradient?
This one? It's gradient.
Why?
Because it's only x, it's R.
Because it is
R2.
R2 into
Or
so this is a function in several variables. Am I right? So we can use the gradient. Also, the gradient is a special case from the Jacobian. Look, Omar, the dimension. So if I want to get the gradient of f or the Jacobian in this case, it will be 1 times 2. 1 times 2, which is the gradient. شو الجريدينت ده بيبقى رو؟ بقى رو. طيب تعرف تقول لي اعمله ازاي؟ partial f, partial x, partial f, partial y. So the gradient vector in this case, يا ولدي, will be 2xy. The gradient vector in this case will be x squared. So, can you do it on the other function? Let's see it in the other function. It's gonna be an f running from r into r squared. Is this sub-function several variables? No. It's a vector valued function. The input is one function, but the output is two functions. In this case, the Jacobian dimension will be باخد الأخير وبعدين الأول. يبقى 2 times 1. طب can you do it? Yes. I will differentiate the given function df1 ودf2 يبقى partial f1 partial x, but there is no other variables, so it's not going to be partial, it will be total df1 by dx, and the second one will be df2 by d of x. So simply it will be differentiating the first function with respect to x, 2x. Differentiating the second function with respect to x is going to be n of x. خدت بالك ان انا هنا ما استخدمتش بارشل ديريفاتيف، استخدمت توتال ديريفاتيف لان هي في متغير واحد. كذلك المعلومات مهمه جدا لانها بتقفل كل حاجه مع بعضها. فاهم؟ اوكي. So, as you can see, now it's running from R2 into R, so f of xy is going to be x squared y. Once more, I will talk about the gradient vector, which is going to be partial f, partial x, partial f, partial y, differentiating with respect to x to xy, differentiating with respect to y is going to be x squared. In this case, I'm running from 2 to 1, so I'm handling the case, but I don't need partial derivatives, I will do total derivatives, because I have just only one variable. So it's going to be for f1, it's going to be 2x, for f2, it's going to be 1 over x, as you can see. Look at these problems. This is running from R2 into R2. So I will need Jacobian. Also, this is running from R3 into R2. طيب, can you give me the dimension of the Jacobian in each case?
Yes.
The Jacobian will be
Times 2.
لأنه R2 into R2. طيب, هنا أنا عندي R3 into R2. لذلك الجاكوبيان هيبقى 2 times كام؟ طيب, هات لي الجاكوبيان ده.
برشا
دي F1 وده F2.
برشا اكس.
بارشل F1
برشا اف 1.
بارشل X. بارشل F1
برشا واي.
بعدين بارشل F2
واكس واي.
بارشل F2. طيب, تقدر تقول لي ده يعمل ازاي؟
برشا اكس.
طبعا ده 2 times 2 times 3. يبقى دي هنقول عليها F1 ودي نقول عليها ايه؟
F2.
يلا, بارشل F1 بارشل X بارشل F1 بارشل Y بارشل F1 بارشل Z سيم بارشل F2 بارشل X بارشل F2 بارشل Y بارشل F2 بارشل Z. Now start substituting, which is going to equal to, let's do it together. Differentiate with respect to X, which is going to be,
X.
differentiate with respect to Y, this one. So it's going to be X squared, صح? Differentiate with respect to X, so it's going to be 1 over Y. Differentiate with respect to Y, so it's going to be negative X over Y squared. Same for the other function. I will start differentiating, okay, with respect to X, which is going to be Z. Differentiating with respect to Y. Do you have Y? You have Y?
No.
Zero. It's 0. Differentiate with respect to Z. Do you have Z?
Yes.
So it's going to be X. Differentiate with respect to X. It's going to be 0. Differentiate with respect to Y. It's going to be Z. Differentiate with respect to Z. So it's going to be Y plus Z. It's really very simple, but it needs training. And it needs you to use your hand while trying to solve these problems. It needs training and solving plenty of problems, as you can see. So once more, this is from R2 into R2, and that's from R cubed to R2. This is going to be the value, partial S1, partial X, partial S1, partial Y, partial S2, partial X. Now that's the value of it. That's the value of H, which is a Jacobian of 2 rows, 3 columns, and it's going to be Z0X, Z0Y, as we did exactly. Okay, this is also another problem. I want you to write the Jacobian for this matrix or for this problem. Of course, it's a vector valued function because the input is how many variable? 2, and the output is how many function? 2 of them. I can write the functions beside each other or beneath each other. It's really up to us. Okay, so also once more, in order to get the derivative, it will be partial F1, partial X, partial Y, partial F1, partial X, partial Y. Then I will take the second function, differentiating it with respect to X and with respect to Y. It's a direct substitution issue. Just to differentiate with respect to X, we'll develop a 2 of an XY. Differentiating with respect to Y, which is going to be X squared plus cosine Y, as you can see. Differentiating with respect to X is going to be e to the power of X plus. Differentiating with respect to Y, which is going to be 3y squared, as you can see. The Jacobian is really very simple, and the application of the rules I believe it is clear as you can see. The second topic that we will be talking with today is the topic of directional derivative. I will make a short stop, then we will continue after 10 minutes or so. Thank you very much, and the best to you.
Thank you.
Thank you.